Hello everyone, welcome to this ARSET training on overview of SeaDAS 8.4.1 for the processing, analysis and visualization of optical remote sensing data for water quality monitoring. My name is Amita Mehta and I will be conducting this training with the help of our guest speaker, Mr. Daniel Knowles from the SeaDAS team. We'll start with a brief introduction to Applied Remote Sensing Training Program or ARSET program. ARSET is part of NASA's Applied Sciences Capacity Building Program, and it provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, and tools. ARSET trainings include a variety of applications of satellite data, and the thematic areas covered by ARSET are given here on the right-hand side. Also, they are tailored to audiences with a variety of experience levels. Majority of ARSET trainings are given online, but often in-person trainings are offered as well. ARSET trainings are live and instructor-led as this one, but there are asynchronous and self-paced trainings available through ARSET website. They're bilingual. In most cases, training material is available in Spanish, and often trainings are offered in Spanish also. ARSET trainings only use open source software and data and accommodate differing levels of expertise. So we'll start with today's session about SeaDAS 8.4.1. We'll have a brief overview first, and then we'll hand it over to Mr. Daniel Knowles for details of SeaDAS 8.4.1, and also he will demonstrate some of the features of SeaDAS. So what is SeaDAS? It stands for Sea, Earth and Atmosphere Data Analysis System. It's a software that was developed by NASA's Ocean Biology Processing Group, and it allows processing, visualization and analysis of Earth science data. SeaDAS is available from OBDAC or Ocean Biology Distributed Active Archive Center, which is part of Earth Observing System Data and Information System, and the relevant links are provided here. As we will see later, SeaDAS has a long history. As new satellites were launched over the years and new sensor data became available, SeaDAS also evolved to include new sensor data processing capability. And the current version of SeaDAS supports the missions listed here. Some of them are past missions, many are current, and there are some airborne sensors are included here. Now, in earlier ARSET water quality trainings, we have used SeaDAS and we have processed data from MODIS, and VIIRS and also Landsat OLI. And what is SeaDAS used for? It's an important software for satellite image processing, specifically for deriving water quality parameters, such as chlorophyll concentration or water surface temperature, just to give you examples. SeaDAS also allows calculations of surface remote sensing reflectances, which are used for deriving water quality parameters. And these capabilities are available for multiple sensors, as we saw in the previous slide. It also offers image analysis and visualization options and allows comparison with in situ water quality measurements. As we will see later, SeaDAS allows statistical and mathematical analysis of image data as well as allows spectral analysis. So why SeaDAS 8.4.1? The current version has evolved with data processing capability for additional sensors such as Sentinel-3 OLCI, Sentinel-2 MSI, and PACE sensors as well. Now, ARSET has used SeaDAS earlier, but the latest version we ever used was 8.1. At that time, in that version, Sentinel-3 OLCI and Sentinel-2 MSI were not available. They became available since 8.3. But the current version includes these two as well as PACE sensor processing capability. More importantly, the earlier version of SeaDAS did not allow science processing on Windows system, virtual machine had to be used on Windows to do that. It was only possible on Mac operating system and Unix and Linux operating system. This version can be installed and used on Windows machine for science data processing, in addition to doing analysis and visualization. So for this reason, we are focusing on this version. A new version, SeaDAS 9, will also be out soon. This will be used as reference because as we move forward and use Sentinel-3, Sentinel-2 and base hyperspectral data for water quality monitoring, we will be using the latest version of SeaDAS. And so it's important to know some of the features of this version now. And that's why this training will serve as a reference for all future ARSET water quality trainings. So that based on that, our learning objectives for this training are that participants will be able to identify expanded sensor data processing capability of the latest version of SeaDAS 8.4.1 for sensors such as OLCI and MSI, use key SeaDAS tools to analyze and visualize water quality parameters such as chlorophyll A concentration, and for that, Sentinel-3 OLCI will be used for case study. Will improve awareness of the plans for incorporating base data processing into SeaDAS. Prerequisites for this training are fundamentals of remote sensing, just to know about basic concepts. And this training, past training about coastal and estuarine water quality, that used SeaDAS 8.1, so that's a good reference as prerequisite. With that brief overview of SeaDAS, here is the outline for the rest of the session. Mr. Daniel Knowles, he will talk about SeaDAS user software, including general image analysis tools and science processing software OCSSW. He will also provide information about reference workflows in SeaDAS for multiple sensors, including those from base. And then finally, he will provide demonstration of SeaDAS workflow case study using OLCI Level 2 and Level 3 data processing. On the training webpage, you will find many extra slides for reference about SeaDAS, but the main focus of rest of this session is going to be on the demonstration of various SeaDAS features. A note about homework here. The homework assignment is posted on the training webpage and it is due on February 29th. A certificate of completion will be awarded to those who attend today's session live and complete the homework assignment by the due date. With that, I would like to introduce our speaker, Daniel Knowles. Also, we want to introduce our contributors, Ainur Abdulrazik and Bing Yang, both from SeaDAS teams. They have contributed to presentation of today's session. So first, Daniel Knowles Jr. is a software developer for the NASA Ocean Biology Distributed Active Archive Center, or OBDAC, and has 30 years experience working in the remote sensing field. Daniel has been developing SeaDAS for the past 10 years. Prior to this, Daniel worked for 13 years running the operational command schedules for SeaWave's mission operations, preceded by 5 years on the pre-launch thermal IR band algorithm development for MODIS. Ainur Abdulrazik is a software engineer at Goddard Space Flight Center's Ocean Ecology Lab and leads the development of the OBDAC's SeaDAS application. The SeaDAS application development team is in charge of application maintenance, developing new features in response to changing needs, and providing user support through video tutorials, webinars, short courses, and an online forum. Bing Yang is a software developer for NASA's OBDAC. She has been with SeaDAS team for the past 5 years, maintaining the application, developing new features, especially for base data analysis and visualization, and supporting users on the Earth Data Forum. Before I hand it over to Danny, here's how to ask questions. So please put your questions in the questions box and we will address them at the end of the webinar. Feel free to enter your questions as we go, and we will try to get to all the questions during the question and answer session after the webinar. The remainder of questions that we cannot cover will be answered in the question and answer document that will be posted to the training website about a week after the training. With that, we invite Mr. Knowles to take it away and provide us detailed information about SeaDAS. Just a brief note here, you will see acronyms, OC, which is ocean color, IOPs, inherent optical properties, RRSs, which are remote sensing reflectances atmospherically corrected, and ROS, or surface reflectances, after top of the atmosphere reflectances are corrected by Rayleigh correction. So you will see that during the demonstration. So now we hand it over to Danny. So Danny, please take it away.
Hi. So I'm going to go over some slides here. There's far too many slides on SeaDAS for this talk, but a lot of these can serve as backup reference for you, because that way we can do a lot of SeaDAS demonstration. So the first slide here is just illustrating the background of SeaDAS and why it came about, back, and appreciation for the fact that this goes actually back into the early 90s. But the main thing is, back at that point when we were just serving SeaWIF's mission, you would get data, and back in that day and age, it was just a chunk of data, and what do you do with that data? How in the world would you be able to visualize it and analyze it? So the original vision, which we've kept up with, was the ability to visualize, analyze NASA products, and to identically reproduce the level 1, 2, 3 data that we distribute. And the other big challenge, which was saw back then as well, to continually evolve with technology, and that is always a challenge to keep up with all the different platforms. And so this is a quick overview of the timeline of SeaDAS, and when it was first released, and that it supported SeaWIFs, and so we've evolved through time, rebranded ourselves in the past year to be the Sea Earth Atmosphere Data Analysis System, because we certainly were supporting more than SeaWIFs, because we're up to 24 missions supported. So and again, I'm going to go through these slides rather fast, because I could get really bogged down on these, and I really do want to demo for you guys. So so here's an overview of what SeaDAS is and does. It takes essentially raw satellite data that gets transmitted down, that we ingest it in NASA's OBDAC and run these SeaDAS processors in order to apply the different calibration through it as we go through, then the products, and then bin it and map it, use ancillary data to help with the atmospheric correction. And all of this is replicatable from the user end. So they basically get the same software tools that they can load on, that you as the user can download onto your computer, and run the same programs that are run to create the data. And additional to that, you can do your own imagery from that, statistics. So it's not only processing of the science to replicate or to make your own variants of these files, but also to analyze and view the images with that. The OCSSW. So this is the part of SeaDAS, which was the SeaDAS science processors that use this. OCSW stands for Ocean Color Science Software, and so it's one of the SeaDAS processors, and this is the official science processor that it's using. And for this processing that's done, we saw earlier how the satellite measures the data, and the data files come into OBDAC. And then what the satellite measurement sort of looks like up top is it's actually, it's got a lot in this diagram, but you get digital numbers out as the radiance comes. You have the water leaving radiance and the top of atmosphere radiance. You have your scan angle, you have your satellite zenith angle and solar zenith angle, and the fact that the sun is reflecting off clouds and aerosols, and you have the foam, and so it gives you a good picture of the complexity of what needs to be done. And SeaDAS is, I'm sorry, the satellite is giving us digital numbers off of sensors, but it has radiance coming in, but we got to back all this out to ultimately where we want to get to the water leaving radiance. This is a repeat of what you saw earlier. You can always refer back to this full diagram. And I'm not explaining every step of the way through it, but you'll see some of it as we demo this. To understand the different levels of file, the key thing to know about level 2 files is it's the native resolution. So it's how the satellite saw the Earth, how the pixels lined up and saw the Earth. So it's not mapped. And the level 2 files at this point have been calibrated, and they've been, the geophysical variables have been added into them, like chlorophyll and cyanobacteria, the sea surface temperature. These values have been added in. We have suites. Actually, we'll hit that shortly. There's some slides on this. So this is a good review slide, though, and it's showing the unprojected file, level 2. And yeah, these are the slides for level 2. So as we go through this, we have what's called suites. So this is called OC suite, which is ocean color suite. So this is a grouping of products that can be processed together. They use the same atmospheric correction algorithm, the same gains, all so that they can be made together. And so they're provided together. There's other ones that could go in here with this, but these are the standard ones that are provided when we deliver a level 2 file. And I think some of these may change with time. Certainly with the PACE mission coming up, they're reorganized in different suites, but just keep in mind that a suite is a grouping of products that level 2 Gen, which is the program that makes the level 2 file, was able to make as one unit. And then there's IOP, it's a different one. So you wouldn't be able to mix and match these. So IOP has different parameters, processing parameters that are needed to make these. So that's the primary reason why these have to be separate suites, separate groupings, separate files. So and same with SST, that has its own processing parameters that are going on behind the scenes. So you need to, when you make these level 2 files, they need to have been made separately. So when you'll find the level 2 files with SST and OC, they're separate. It doesn't mean that later you can put them together for mapping, but just keep in mind that they will be separate. So these are the idea of what is some of the things that we provide right now. And each of these level 2 files has flags, and we'll illustrate that a little in the live demo. So this is a listing of flags that you can come back to. It's that each pixels not only has its chlorophyll value or whatever the actual data value, but has this additional value to indicate the quality of the data. Point about native pixels. So this is they're gridded as the native pixels. They're not remapped. Atmospheric correction is applied. So this was the process of getting from the measured radiance at the top of atmosphere and backing it out to get the water leaving radiance. And you have all these parameters that can be derived through using ancillary sources, the MERA data, and for SST we have this source here, and you're backing out things like wind speed, ozone, concentrations, all of this goes into that. That's assessed through these ancillary data files to ultimately determine all this to back out that. There's also vicarious calibration. So when we've calibrated the data with onboard calibrators, we ultimately get to a certain value, and then we've looked at over time vicarious sources, and there can be a gain adjustment factor that is determined and this isn't this would be determined pretty early in the mission and would probably stay during the mission. It's not something that's just changing every year or anything like factor. And this is just an awareness that if you have an elevated lake, that you would have to adjust where the lat and lon of that is, and it's just giving you, an appreciation more of the fact that when the sensor's looking at the Earth, it's got to figure out what latitude and longitude it's actually seeing. So all of that goes into the level 2 file. And then the next phase of processing, if you go beyond level 2, is at that point you want to you would go beyond level 2 if you either want to map it or you want to combine a bunch of files together like this to create a monthly. And so the next phase of the step towards that would be binning them all together. And binning is a form of mapping where we've divided the world into equal area bins, as we call them. It's a sinusoidal projection, and you run the level 2 file through the binner, and it will take the pixel wherever the pixel is and put it in the appropriate bin that it goes into. So it's and you can just bin, like if you do a monthly, then you would take 500 files or however many files were that month, and you just run them each through. They would keep being thrown into the bin, and it would accumulate over time or over your processing till you fill up, till you finish all the files, and then you would have these bins. So when you during the binning step, we're dividing the world equally up into increments, and so we divide it into like 1 degree increments, and anything divided by that on the latitudes, you're dividing it evenly up, and you end up with numbers like 58 meters and 4.64 kilometers. That's just how it divides out into the world. So that's your resolution, and you don't want to be thrown off. But when you see we release 9-kilometer and 4-kilometer data, that's actually 9.28 kilometer and 4.64 kilometer data. And then the next step after you've binned a file is to map it. And above is showing the level 2 file, and then that's what it looks like mapped, that same file. And below is mapping, where you've taken hundreds of files to make monthly. So with mapping, you have much more options. You're not really restricted in dividing the world up in the little equal areas. You have tons of projections to choose from. The default is plat carré, which is vertical and horizontal lat-long lines, which are evenly spaced, but they're not equal area. And we'll get into that later, because it's not a good projection to use for statistics, but it's the projection you tend to always see people display, unless it's an atlas or something, they'll display in different projections. But we will get into other projections in this talk. And This is a slide that's kind of helpful in determining, do you want to use the files that we provide, or do you want to use SeaDAS to generate your own files? This is beyond the visualization aspect. It's just, do, do you, are the files that we're giving you good enough for your purposes, or do you want to process them? And so these are parameters that help you know whether that's what you want to do. And so basically, there's limited geophysical products, so there's more available. So if you need products that we don't provide, that's a reason why you would want to process. There's other ancillary products as well, same concept. There's flag thresholds. So depending on um, if you want to adjust the flag thresholds of when something triggers, like say satellite sensor zenith angle, triggers at 60 degrees usually for most sensors. And if you want that at 40 degrees, that's something that you would have to run level 2 gen in order to you would make your own file to do that. And there's more resolution choices in modus anyway. As far and for binning, there's many resolutions available, whereas we only have the 4 kilometer that we supply because it's a global product, and 4 kilometer is a lot of pixels globally. So if you have a region that you want in 1 kilometer or 300 meters, depending on the instrument, then you would want to do the processing yourself. Any time resolution. So if we provide a monthly, but if you want like a 2-week file of a certain time period, then that's something that you would have to do separately for processing. The big pro on the blue is the pros. What you gain is for OBDAC. It's already processed and already available. That's the key. It's like that's where OBDAC wins. Is it's already there and ready. So if that's sufficient, then that's good. And it's also referenceable, but you can certainly reference that you ran the SeaDAS or OCSSW processors, but when you actually use a file that we provide, then you can actually reference that exact file. So that can be helpful. And then for the mapping, we provide global 9 and 4 kilometer resolution files, but so there's a lot you can do, and this table is meant to help you make that decision on whether you should or shouldn't, pursue learning to do the OCSSW SeaDAS processors. So we've got some reference workflows here. I'm not going to spend too much time on this because then we can do our own live demo. Actually, these are really reference ones on all the missions. So you just come back to these as you need them. They should be helpful because it can just help you know. In the light blue is the name of the processor, and the green is the name of the file. So just to walk through one, which will be like Ulchi, which is what we'll do today. This is only going through level 2 gen, because after level 2 everything's the same, but before level 2 every mission can be potentially different. So an example of Ulchi is you have a level 1B file, and that's the actual name of the file there. So it'll have a file name that'll be buried in a directory. So that would be your input file, and then you would add an ancillary file if you choose to have ancillary data, and then you run it. So that's a very simple workflow, whereas VIIRS would be a little more complicated, where you have to take the level 1 file, you have to geolocate it to make a geolocated file, then you take those 2 files, then you calibrate it to make a level 1B file, and then that serves as the input to level 2 gen along with the geo file. So VIIRS is a little more complicated, but that's what these workflows can help you as reference. And we have a binning workflow as well. So this you can just refer back to this, but this is just showing that you can bin um, the files together with level 2 bin, or you can you can bin them all at once. Like say if you want to do a monthly, you could take the 500 files and bin them all together into one bin file, or you could do it by this route where say you did you bin those into daily files, and then you had for your month you would have 30 or 31 daily files, and then you take those and then you bin them to create a monthly. And the advantage you would have over this workflow would be if you want to then later go back and do it like a 5-day span or a 7-day span. You already have your dailies bin, and it's really quickly to bin them from with level 3 bin, so you don't have to go back to your source 500 level 2 files or your entire mission or whatever you have. So this is like a good if you have a lot of data to work with, and you can even do this on a single file basis. So if you have 500 files, you could bin all 500 files into separate bin files, and then subsequently you could then get rid of your level 2 files and then and then you can bin whatever files you want together in the level 3 bin. So it's one of the options. This actually kind of reflects on what I was talking about the dailies and monthlies. There's a program called MapGen. I won't get into that too much, but that's just a wrapper program that will help you create true color images from a level 1B file or other images. That's showing you the inputs and outputs to it, and behind the scenes, MapGen is running multiple ones of the processors. Like it'll run, it'll bin it and map it, like the L3 bin and L3 MapGen. L2 gen can be buried inside there as well, depending on the input file. And this is a idea of what it's like when you run a file from the GUI. So this is L2 bin GUI. So the GUI, you fill out parameters within the GUI, and then you press run. And when you run it, it will create a PAR file. And then that PAR file will get run. And at the command line, you're not at the command line, but it runs this command, which is L2 bin PAR equals the PAR file. And then it writes that PAR file out, and then you can go back subsequently if you want at the command line and rerun it because the PAR file is there, or tweak the PAR file, or write your own PAR file and not use the GUI at all. But the GUI serves, if anything, as a really good tool for formulating what you want in the PAR file, doing a quick test for a particular scene to run it. But once you start getting the point where you're going to do entire mission of data or hundreds and hundreds of files, then you may end up not using the GUI after you've established what the parameters are you want. But you still can use the GUI, because for this particular tool, L2 bin could have a text file as its input, which contain 500 files, level 2 files. So it can do a lot from the GUI. So let's take a quick look at a demonstration of processing with SeaDAS, the SeaDAS science processors, an ULCI image or set of ULCI images. And we will look at this more detail in the live demo, but these slides are good reference. And I just want you to be able to follow along with slides, and you can look back on these. And there's actually another workflow later in this slide deck that you can look at as well. I'm not going to go over it, but so here's an example where I take 6 files, level 2 files. I've got 3 Sentinel-3A and 3 Sentinel-3B files of level 2, and they're all from the same day. And we take all these files and we put them together into a file that it's just a text file. So the contents of it are just the names of these files. And I have those files in my same directory that I'm running this from. So I run L2 bin, and I'm going to create a mapped file of these 6 Ulchi files. So I open level 2 bin, and we'll show you how to do that in the live demo. But you can refer back to this. So here's my input text file list and my output file, which is going to be a bin file. It's called cross sensor. Usually you'll have a sensor name, but since it's multiple sensors, it's cross sensors the default that we use. And so we up at the top are the instructions. Select the I file, so that's done. Next is select a product and a prod type. So here we're selecting chlorophyll A, and prod type is regional. Prod types can be like daily, monthly, if you want to have like binning by time frame, but if it's just without time information that you just want to bin them all together, then regional would be the one to use. And you can specify a resolution. The resolution of these level 2 source files is 300 meters. So there's nothing stopping me from picking 300 meter at this point. But to run, you're usually best to run things to begin with at low resolution, especially high resolution things like that, just to see the output, and then you can then you can up your resolution and it'll take longer to run. But I always like to start with low resolution just to get a ballpark of if this is what I want to do. So then you add in your flags, and there's not much room to see the flags in this current release of SeaDAS. The next release, we will have a giant window where you'll be able to see all the flags. So one of the improvements that will come with I probably didn't mention, but we will be releasing SeaDAS 9 in conjunction with the launch of PACE. So that should be February, March timeframe. So it'll have some fixes and some improvements. And that's one of the improvements, that you'll be able to see all these flags there. So we've added all the flags. This is a big list. This is a huge list of flags that basically when you're bending it, you can barely see it, but high glint's there. So it's basically saying if it's high glint, don't use that pixel. So we run it, and that would be the output you will get, that it created that file. And once it's created that file, like I said, you can't view that file, but the next step, you can map it. So I've running level 3 map gen, and here my input is that. The little B there is for bin, and M is for map. So oftentimes your bin file and your map file names look almost identical, just a B and an M. But you might add some information in your mapped file regarding what projection you're mapping it to, things like that. So we just select the I file, and then we want to select the product. If you leave the product blank, it'll actually map out all the products that were in the bin file. So one option is to leave it blank, but you can specify a product. You need to make sure you pick a product that was in your bin file. So if you happen to bin SST, and then you're trying to make chlorophyll, but the bin file only contained SST, then obviously that wouldn't work. So this needs to be a subset or all of the products that were in the bin file. Plat carré is the default projection, and we've selected 2 kilometer, which was consistent with what we binned it at. And I have nearest neighbor selected here. I think that might be mentioned next. No, it's not, but nearest neighbor, it just means you don't interpolate the pixels. It's much quicker. And again, this is what you would do for your first round to get an idea of things, and then you go back and make it more detailed. And that's what I've done here is I changed from nearest neighbor to area for interp. Interpolation is what interp is. And so area will take a little longer, and so that's going to do interpolation between the adjacent pixels. And we run it. And so this is 2 kilometer. So this is the file that was formed. Now, the fact that it's 2 kilometer, this is a huge area actually. So the 2 kilometer isn't bad to run with, but you can certainly run this at 200 meters. So you basically have to the left Sentinel a 3A, and to the right was Sentinel 3B. And this was a cherry-picked scene because you actually get the entire Gulf of Mexico with virtually no clouds. So it's a kind of a unique scenario to find that situation. So so this is a huge scene, and like I say, you could run this at 300 meters. It just takes longer, and then when you view it in SeaDAS, it takes longer to load, but you can potentially do that at much higher resolution. And this illustrates that actually I ran it again and mapped it at high resolution, and you can zoom in on New Orleans and see that at 300 meters. And this is a slide, so it's actually probably zoomed out even right now as far as what you're seeing. So SeaDAS is going to support PACE, which is coming up, as I mentioned. And it's one of the reasons why you're going to want to update to SeaDAS 9. I would always encourage you when we release SeaDAS to update, because we're not just doing cosmetic changes. We do bug fixes, and we're adding useful tools. We're not just moving things around. So it's really valuable to get the latest releases of SeaDAS. So 9 will come out soon, and it will support PACE, and PACE data access is available here. We have the simulated data right now. On board PACE is not only the OCI instrument, which is the ocean color instrument, but you have some polarimeters. So this shows within SeaDAS 2 of the polarimeters imagery loaded in, a HARP 2 and a SPEX 1 that's been loaded in. There's an angular view for polarimeters. They have angles, and so you have options to view. There's a tool that similar to the spectrum view that we showed earlier that will view across the angles, so you can see the values across the different angles and the angular shape that it makes. There's an animation tool in there, so this isn't limited to PACE, and it's not limited to angles, but you can take a set of bands and animate across those bands. It was originally envisioned as a way to view across angles, but it can certainly be used to view across wavelengths as well, or across time as well. So animation is pretty straightforward that it's animation, and so it's animating these bands. So it has a lot of uses outside of the polarimeter. This may be, yeah, this is an example of if it'll play. Yeah, so here's an animation, polarimeter animation where it looks like it's only a few scenes, but you can see the color bar, and it's showing the actual when you run it, you can slow it down, so but that gives you a good idea what the animation can do. Maybe we got more here. So you've got the pins that you can put in there. Okay, and so the pins enable you to determine as we showed before, the angular view, and you can animate across. Yeah, I showed this before where you can have the angular view presented on a plot, but you can actually animate that as well. So we'll play that, and then there we go. So specs one animation. Just illustrate an animation of specs one. This is a really powerful plot that shows the spectrum view we saw before, where in the past RRS we had a few points. This is simulated data, but you can see very clearly that once you go to PACE with the hyperspectral instrument, that you're with the spectrum view, it's going to really hone in on species of phytoplankton and really tell a more detailed story. So that's an example of PACE simulated data in the spectrum view, where you see so many points and so much shape to this. Okay, this portion we're going to do the live demo of SeaDAS. And to start with, we're going to have a data file that we'll work with. So we have the Ocean Color website. To get the data, go to Data, Find Data, and I'm going to use the level 2 browser here. Oh, it's a pretty sophisticated browser. It's aged look, but it's very powerful. So I'm going to select the Sentinel-3 missions. I'm going to, as I look for the matchup, I'm going to be aggressive and say I want the scene to fully match up just to reduce the retrievals. And I'm going to click reconfigure page. This just makes sure that all the parameters that I set for the mission are in there. You may not have to do that, but just want to make sure. I'm going to pick the date, July 12th. Right now, we're at July 12th. Everything's there. And then I'm going to pick the Chesapeake. Go down in here, pick the Chesapeake Bay, and I'm going to do the amount that is displayed at a bigger number so I don't have to tally through. And then this should come back. Let's try that again. So July 12th, and this is the file. So this is the level 2 file, and this is the level 1 file. So you would download both those files, is what I did. And then that's how I get at the data. Then to launch SeaDAS, there's several ways of doing it. You can click on it. I'm on a Mac, so it could be different for you, but I'm doing it from a terminal window, essentially. You could open a terminal window and launch it that way, or you can do like I did and right click and launch it as a command to run inside a shell. I'm doing it this way. Or you can just click on the icon itself in the dock. Sometimes, though, when you click on the icon itself, you might be missing some environmental parameters that are helpful for when you run the processors. So this is a little trick to get by that, but it's only for the processing. That's how I'm going to launch it. And the advantage of running it through a terminal window like that is that it leaves behind a terminal window, and when things go wrong or something, a heap dump or something happens, it'll write to here. So it is a bearing on things that happen, but you don't have to launch it that way. It's just the way I find that it behaves the best, especially with the processors. So I have this SeaDAS loaded in, and I'm going to load in a file. And we'll start with loading the level 2 file that I downloaded. So down here it says it's reading the file. It's a level 2 file. It's rather big. It's ULTRA file. So this is the full file, but I want you to see the full file before we look at subsets of it or expanded versions of it. So what you get is you got the RRS and chlorophyll. So let's open chlorophyll. So this is the full scene of it, and there's plenty you can do, but what I'm going to do is I'm going to use an extracted scene. We'll go over later some of the processors to get to these extraction points, but I'm to make this thing run quicker. It'll run fine as it is now, but I can demo this quicker with an extracted one. So let's close that just to give you the idea of the full file. And in fact, I will show you how I made the extract. I'll kind of mix it in a little bit. So to make an extract, and I'm going to come back to level 2 gen a couple times, but really quickly to show you how I made an extract is that I had loaded, as I mentioned, that I had downloaded that bigger level 1 file, and I click, if you see that flowchart earlier on the slide, you load this file in to level 2 gen as the input file, and it's going to give me an automated name out. And I can pick different products in here. This is the default products. So I can go through here and there's this thing called the wavelength toggle selector or limiter. What we'll do is we'll say we don't want wavelengths outside of 865. And so then if I set that up this way, then if I go to the radiances, say RRS, I'll open that up and we see that the defaults are here, but what this has done is it's a 3-way toggle selection control. So now when I click this, the first click will fill it out with all the wavelengths that are here. Second click will fill out with all the wavelengths, and then the third click removes them all. So it's a 3-way toggle. It's a quickie to help you with that. So, and they fill out down here. So you have RRS VVV, which means all the visible bands, and these are outside visible, so these got added in. So this is a product list. And so I've just increased my products. Before it said RS VVV, now it's added all these on. So let's say you want also the ROASs, which are the surface reflectance bands. So same thing with that. First click gives all of these bands here, and that's what I want. If I did more clicks, I would get the full thing or remove them. So I'll go ahead and add those in. And these are radiances. In here we have some derived geophysical parameters like chlorophyll. So we can go through here if there's anything I want in here. I just have to be careful not to click things that are conflicting. But that can take time to figure out which ones you can add in. In general, you can add them in, and we can go over that a little bit. But as far as which products go together, like the inherent optical properties, products, you don't want to pick any of those because they don't sync up with the chlorophyll. Sensor zenith angle is a really good one to pick. That's the angle that the satellite's viewing. And I think there was cloud albedo. You can click that one. We'll talk about this later, but you might click these aerosol models here. Click whatever you want. You can also, well, within reason, not whatever you want, but whatever syncs up. We'll come back and talk about the aerosols and some of these processing options later. There's also subsetting, so we can subset this file down to just the Chesapeake. If I go back to the main menu, this shows the L2 prods that I picked. I have the ability to get the ancillary data. If I run it just like this, it's going to use default climatology data. It's not going to get all the MERA measurements for ozone and whatever other measurements that can help with wind speed corrections and everything. So if I do get ancillary, click here and do get ancillary, what that'll do is it'll go out and it'll pull the ancillary files onto your machine, and it put them onto your machine in these locations, and then it's telling the level 2 gen that this is where your ancillary data is. So at this point I can run it, or I can save out the par file, or I can load in par file. What I'll do is I'll load in a par file, and I've already created one. I could run it, but I'm going to just load in the one that I'm going to demo. And So because I've saved some of those out. So this one that I'll demo is this 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 one right here, which I just named multi products of Chesapeake. So I load that in. I clicked the load to load it in. And so what that just did is it loaded in the par file that I had run earlier. And so this shows you what I'll be demoing this file. So this is restricting to the Chesapeake. So what we're doing is we're having a bunch of products, which makes it a heavy file, but then we're limiting it down to the Chesapeake, so that helps reduce processing. Well, not the the processing time, but it'll help with the visualization. And I've thrown in a shallow water depth of 2. There's a coastal flag that's at 30 meters. This may or may not be of any use to you, but it just enables you to have a, that would be a 6-meter flag, since we're just going to look at Chesapeake, and everything in the Chesapeake is, nothing's less than 30 meters. So that's a useless flag. So if you want to override that flag with the shallow water depth of 6 feet, that enables you to flag out things that are 6 feet or less. So it might be useful. Then we would run this, and then that creates the file that I'll show you. And I just want to show you, yeah, actually, there's a variant that I made of that where I just did the Chesapeake, but with just chlorophyll. And I probably don't have that in here, so that's not a worry, but it's that same file, but just with the chlorophyll, so I don't have all the other products weighting it down. While we're on this, an easy one to grasp, another subset would be the surface reflectance one. So if I load that one in, this one, I guess it's the full scene. But this is an example where I just have 2 blue bands and a green and a red band. So that's a nice option to have for making true color images. And this is a suite called SF Ruffle Surface Reflectance. So that particular suite, if you run it this way, it'll run much faster because you don't have to do aerosol correction for doing the true color imagery. So it is helpful in making files that are smaller. So if you want to do true color imagery, you don't necessarily need to do with a file that has 50 products in it. You can have the separate one. So, and so that's how I create these level 2 files, or most of them that I'll show you. And I'm going to demo some of these files now. So I've got level 2 file, and what I'm going to do first is just demo the really light one. And the light one is just Chesapeake and just chlorophyll, because I just want a file that is really quick and easy to work with. And then we can look at some of the other products as well. So we have the chlorophyll band, and when I click on it, it opened the chlorophyll image. And so these are all layers, and you see they're all stacked here as layers. We also have, this is level 2, we have all the masks available. So we have a land mask. We turn that on, we see the land mask. We can zoom in, since this is and we can, since this is 300-meter file, if we, in the navigation window, we can pick pixel, and that's going to match the pixels of the file to the pixels of your computer. So that way you get an idea of the resolution of your image. And you can see nuances along the coast where you have chlorophyll, and that looks good. But then if you zoom in at the Potomac, the data starts not looking potentially right if you know what you're looking at. And so what's happening here is that that's actually data that had aerosol algorithm where it exceeded the maximum iterations. And there's flags here like this. They're kind of buried in here, but you can expand that. So the aerosol removal exceeded the maximum iteration. So basically that's bad data, at least as is with that current aerosols done. So you can certainly set the transparency to 0. That kind of hides it because so if you're using this file as is with those aerosols, then you don't want to use that data because that's flagged data. So that gives you an idea of that flag. There's also ATM warn, which is a very similar one, atmospheric correction warning. So that's why that data is looking a little not to be expected. We'll look at shortly how to change your aerosol correction. This is the default, and it's the one we recommend doing, but because it's going to apply to all the scenes, but you're going to lose that data. If you really want to try to gain some data back, then you'll need to, on a scene-by-scene basis, go through the aerosol correction manually through picking the different models. One issue with this scene that is the high glint. If I look at a true color image, I'll come back to this scene, but I want to show you the same scene in true color as a full scene. So as opposed to just the Chesapeake, just so you get a feel for what happens with the glint. We saw this in a slide earlier. So if I take this scene, I've loaded in, and I'm just going to straight up make it, it's just got the true color bands. I'm going to make a true color image. It's looking for the bands in it. This will change, and there won't be as many choices of, it's all the same. The sensors using the wavelengths. In 9, it'll be a little less, but basically it's finding a profile that in order to map out the true color imagery, and that will open this. It takes a little while, probably. Yeah, there it comes. So just have to be patient with this. I'm going to go with Color Manager right now. It's on the statistics of the band, although this is pretty much, you get the ideal of it. I don't really need to tweak it, but ideally you would have the range for red, green, and blue be even range. And the best way to do that is I've got this A to B button here. If you aren't A, you click A to B and you're on red, it makes it go from 0 to 1, or I've changed my defaults to go to 0 to 8. And then I just go through each red, green, and blue band, and I click the A to B. And that just makes sure that your red, green, and blue band are all mapped identically. But when you map it on the statistics of the band, it can pull out things, but then your true color image would vary based on what's in the image itself. So you want a standard, and in SeaDAS 9, that'll all be by default. And so we can zoom in. So we see that Chesapeake's actually pretty good, but we got a ton of glint to the right. And that's the importance of understanding the satellite. Whatever satellite you're going to be using, you want to understand that satellite, especially regarding glint and regarding what is nadir. So you would normally think glint should be in the center of a satellite scene, but Ulchi is tilted 12.5 degrees westward. So that's why the glint is actually off to the side of the scene. And this glint's only going to be, where it's in the near the subsolar point. And so the actual nadir point of Ulchi is somewhere around here. So because the sun is also over that way. So not only is Ulchi tilted, but the sun is over there. So in general, your Ulchi scenes where there is glint are going to be to the right of the image. So if you were to look at the chlorophyll image, you actually get good retrievals even in this glint area, but they're actually not good. They're compromised. So you have to be careful about that. So when you're picking an Ulchi scene, you want to make sure that the area that you're using is not in glint itself. So this is a good scene. And lastly, about understanding the sensor is when I mentioned nadir, that's when the sensors pointing directly at the ground, that's when you have the highest resolution. So if you get a ultra-scene where the area that you want is just right to this area of the image, that's where the lowest sensor zenith angle is, you'll get the highest resolution, which is 300 meters. But if you're over here, then that's a higher scan angle, and so you're looking probably more like 750 meter pixels. So the resolution degrades. So the key in understanding sensors is knowing where the glint might be, and knowing where your good images are. So, and then that was a example of how you make true color imagery. So I'll close that product, because it's best not to have too many products open at once, although you can, but then it can bog SeaDAS down. So we've seen all the different layers, most of them. There's I'll show you these when we go to mapped images. Actually, there's a landmass and a bathymetry one. But there's a tool that we call the soft button, and it's up here. So what the soft button does is you can click on each of these layers individually, or you can use a soft button that actually will do it all at once. So if I click it, it has two steps to it. This one, it turned on the annotation layer. I'll just toggle it so you can witness how it. So you have one where it zoomed it out and turned everything off, and then one where it zoomed, out this time and turned everything on, or many of the things on. So this is basically an assignable button that I'm just trying to drag this here. So the controls to that button are up in the preferences. So it's a layer button. And if you go over here and find soft button, then these are all the things that it can control. So you basically set your desired behavior of this button. It's a nice little shortcut button that you can pick your favorite things in these two toggle states, the first and second toggle state. So in this case, the first time I click it, the map grid lines go on. The second time they go off. If I can do on, then for every click they stay on, but other things go on off. So it's a nice way if you have many buttons that you continually having to click for a scene. It's a nice new shortcut way, which is called a soft button, which basically you're assigning a bunch of actions to a single button. So we'll leave that. And next thing we'll take a look at is mapped images. So to get from level 2 to level 3, we mapped it, and we're going to go with first. I'll show you how I mapped. I actually have to hit level 2 bin on the way to mapping. So I go to L2 bin, and I'm just going to go ahead and load a par file in. So if I go up, navigate to my directory where I stuck some of my par files. I just named the par files with the L2 bin in front. So I have a par file. This one was full scene. That doesn't matter. I'll just open that one and show you what that is. And that loaded in. So what that has done is, and I don't think it, yeah, so I have to actually, I didn't save the I files in my par files. That way they're more universal. So what I have to do is select a bin, one of the level 2 files. So I'll pick one of the level 2 files. I'll get the one that the chlorophyll one that we were working with, pick that as the input and output. And now those parameters I loaded in are applicable. So basically it's going to take whatever's in that that level 2 file, which was just chlorophyll, and it's going to run it with the flags that got set here, which I had in my par file. And then I would run level 2 bin, and then after that I would run level 3 bin, level 3 map gen. And again, that one, I would need a bin file up here. I'm not going to bother picking that. I think you can look at the diagram to see that, but I'm going to just show you the parameters. And that's the So now we're going to map. So this one will do this particular mapping here. So this is one mapping where this is actually, I would load a level 3 bin file here. I'm not going to run it, so I'm not going to bother doing it. And so this has a projection in here that is, I'm using a Lambert equal area projection for the one I'm going to show you, but we also could select Plat Carré as well, and I'll show you that as well. And then I have a resolution of 250. If you remember, we were limited on our resolution based on the equal divisions of the Earth, so that 300 isn't an option. So I'm going, since Sentinel-2 is at, I'm sorry, 3 is at 300 meters, I'm going a little bit better than that. And I'm using area interpolation, so that will help fill in any missing pixels that, because of my higher resolution, I'm picking. And it takes a little longer to run, but not too bad. And in this case, I've actually set a regional bounds on it. You noticed before I had set regional bounds in the level 2 file, and so this one I've also set them. When I make level 2 files of regional bounds, if my region is, whatever my region is, I increase the region size by half a degree in every direction to make sure that when I'm running level 2 gen, that level 2 file has all the pixels that I need for the mapped one. So this is more precise when you're at level 3 map gen. When you were at level 2 gen, you just want to reduce the size of it, but you don't want to try to get it exactly the size that you ultimately want to get to. Because of the mapping, you'll end up losing data. So I'm not going to run it, but now you can go back, look at those, look at the slides to get the idea. And now we're going to look at those files that got created. I've got some level 3 files, and I'll be providing some of these level 3 files that you all will be able to use and to demonstrate with. So even if you don't create them, it gives you files to work with. So 2 key ones I'm going to open. I'm just sticking with chlorophyll right now to keep a light file, but I can map it with other ones. I'm going to close the source one just to keep my software light. The less files open, the better, especially when you demo something. So that way, now these are map files. Before I show these to you, these don't contain land masks in them. And one of the tricks we're talking about 250 meter resolution. This is getting to be a bit of pixels, and then we want high resolution land. So we're going to put the land right now before we open these. So I've selected the file, and I have choices of 1 kilometer, but that's not very good. So, but I can up that to 150. And the reason why I'm doing this is I don't want the SeaDAS to freeze. But if you select 150 or 50 meter, it's going to be a lot more pixels to work with, better resolution. I'm going to reduce the super sampling factor to 1. I'm only doing that because of this being Ulchian. It's a big file. And it's beyond the scope of talking about what these mean. But if you reduce this to 1 and this to 1, it'll give you the better chance of this not freezing up. And I'm not going to have this enabled. Most likely you don't have to do what I'm doing and it won't freeze up. But you will find when you're putting these 50 meter and 150 meter on big files, because of the resolution issues, it can freeze up. So I don't want to freeze up. So that's the workaround. But to that, so I'm doing this in both files first, and I'm also going to put the bathymetry there again before I view it. Ideally, you would probably want to view it, then decide later whether you want to put it. But I just want to make sure that this works and doesn't freeze up. So I just put some bathymetry in one of these files. I don't need it in both of them because I'm going to demo this one mostly. So here we have Plat Carré. That's the standard projection. So let's take a look at that. And as I said, I made these coast and land masks, which actually created these water fraction band. If I toggle that on, so we can see the land. So this is now 300 meter, or actually 250 meter file. So that's been reprojected at 250 meter. And I want to view the other one that I did, which is Lambert equal area. So the key in that phrase is equal area. So let's take a look at that, and I'll put the land on that. I'm gonna use this soft button to, when that made it big, it actually, because my soft button was configured to turn the land off, but what I want to show you is the difference in shape. So, so now when we compare these two, you see the drastic difference in shape of the Chesapeake if you use what's commonly used is these the lat lawns, where it's a vertical horizontal lat lawn that's evenly spaced, where in reality the Chesapeake is more like that. This is the equal area gridding, whereas this is not equal area. So every pixel's not equal area, especially as you go north to south. So it's okay to present this in general, unless you get up to the North Pole, and in case this gets stretched out incredibly, but you don't want to do statistics on a file that's not equal area. So for statistics, you definitely want to use this, and then for displaying images, ideally something like this. It's just up to what your time and resources for mapping. So to do statistics on this, one thing we can do is we can pull in a shapefile for the Chesapeake. So I've pre-made some shapefiles. So import vector data Esri shapefile, and you can make your own, or you can. There's plenty of them out there for. I can pull them in for Montgomery County or for Maryland, whatever you want. But this it's a simple shapefile that I actually just drew. To draw a shapefile, you would just click on one of these drawing tools, and you would draw the region you want, and then you can export it. And the way you import and export into a file, a particular shape file, is once you've made it, it's right here. If that's one I made, then I just right click on it, and then I export it geometry as shapefile, and then I can save it out. So if it's one that I made, that's how I made this, and then export it and import it in. So what do I do with the shapefile? So it looks kind of arbitrary, but it covers all of the Chesapeake. And so then what I can do is I can do a mask on this. And so what I can do is a mask that in the mask manager, f of x. If I go over here and I look at just the masks, I say, well, I'm interested in just the Chesapeake. So what I can do is say, I want it to be Chesapeake. And then I say, and you can either do this and or that, and then you do not and not land. So I want it to be in Chesapeake and not land. So now I've just made a new mask. I'm going to give it a name. Just call it Chess Mask is the name of this mask, and I will make its transparency 0, make it stand out, and give it a different color. I'll give it blue. And then if I turn off, there's a vector masks. If I turn that off, now I can see that I have a Chesapeake mask that's the region of the Chesapeake only that's in blue. So it's not the color that you care about, but you want the mask itself. So what you can do then with that Chesapeake mask is you could limit your data on that. So if I click on the chlorophyll over here, right click, go properties, and then if I do valid pixel expression, if I type in chess mask, what I've done is I said my data is only valid if it's in that masked region. So that's called a region of interest mask. It's the mask is representing the region I want. if I want to use it as a flag mask, then you just invert that, and I would just say not chest mask, and now the data is outside. So that is one use of that. Let's go back to putting it as the data inside. So another really nice thing you can do with the mask is I have this region of the Chesapeake, and I might want to say, well, how big is that? So to do that, you go to raster, masks, and mask area. And I can pick the mask that I'm interested in, Chesapeake mask, and run it. And so my mask area is 12,000 square kilometers, which is fairly consistent with the values you find on the internet. It's a tough system because of all the tributaries to get exact match. I think the numbers on the web are like 11,600, but you've got all these rivers and everything's at 50 250 or 250 meter resolution here. So you're not going to get an exact match, but it looks like in the ballpark of at that resolution of what the actual values are. And that's the region of the Chesapeake that you're interested in. And so then I can say, well, let's do some statistics on that area now. So I go up to this here, and I have to, if nothing's selected in here, that means you don't have a band selected. So right now it's kind of in nowhere land where nothing's really selected. So just kind of click on that, click on your statistics, and I'm gonna limit my region to be water and Chesapeake, and I'm going to say, give me the intersection of that. So it's going to look at just that as my region. So it's going to ignore the land around it in the values. And then I run this. And then what that's showing me is that the number of regional pixels. So I'm getting a retrieval rate of 46% of my pixels in this Chesapeake region have values, which looks reasonable. That looks like what it is with all the river systems there. So as I mentioned earlier, there's plenty more we can do. I want to show you the aerosols, but I do want to show you this a few things up. Sorry, with bathymetry. Let's look at bathymetry, and I have my bearings. Let's put on the land mask. And what can we do with bathymetry? Well, one thing we can do is we can mask on that, and we can also create contour lines on that. That's a very useful thing for us to do. So what we could do is let's say we want to do one at, this is in meters. So I'll do one at, say, 10 meters. And let's say I want to do 2 sets of contour lines. I do 2 levels, preview it. And my first one is here. Actually, I'm going to go back and I'm going to say that the last one is just so it'll be less work on my part. It'll auto make that. Now I have 2, one's at 10 and one's at 200 meters. And let's go ahead and color one white. So I have 2 sets of contour lines that'll be created. There they are. So we see the one along the Atlantic shelf, and we have another shallow water one that's going into the Chesapeake. So now if I want to see that on my actual data, go back to the data, and these are here. The contour lines are layers, so they're right here. And if I'm in the right file, hold on, let's see, that was not on. Okay, so I don't need the polygon. So now I can see these contour lines here. And then I could limit the data based on depth instead of being in the Chesapeake Bay. So if I want to go back to chlorophyll and I want to say bathymetry less than 200. So now I have my shallow water bathymetry less than 200, and I could bound it inside the shallow water as well. So bathymetry less than 200 and bathymetry greater than 10. So that bounds the data within that particular selection. So there's a lot you can do in combination with the masking and the contour lines. If I want to do quick extract, like say you're interested in this area here, you can just zoom in, do an extract here, click OK. I just click that tool there, which is the extract tool. Take a look at it, open it up, and so now we're extracted here. We can add the color bar, the map grid lines, zoom out, and so now we have a zoomed in field and zoomed in image. There's a co-location tool. Co-location tool enables you to take multiple files and combine them together. For that, good example of that is, let's look at, we got the there's some products I mentioned you can't put together when you make them, so later you can put them together. So let's open the cyan product. So this the cyanobacteria levels. We zoom in here, we can see the cyanobacteria. It's not in every area, but it's been detected down here. So that's that this file would not have been able to be combined with chlorophyll. So what I can do is, now that it's mapped and already processed, I can combine them. So if I go to co-location, and the products are already loaded in, so sorry, you want to pick them. So I have one that, and they do need to be ideally the same mapping. You don't have to make them, but the advantage of making them the same mapping is this tool and other tools work better when you want to combine them because they're the same mapping. So I've got my chlorophyll is going to be my main one that's serving as the map. But since it's the same mapping, it's not a problem, and it runs faster. So basically, I'm trying to combine these two files together, and it's going to be called collocate, but I can change the name. I'm not going to bother, and I'm going to run it, and I don't know how long this takes, but it should be relatively quick. Some of these tools enable you to go talk about other things while they're running. Other ones lock it up, but that one does, but it's finished. So then it just made this collocate. So now what it did was it appended, I had some options to not have it append some things, but to the sources that came from what's called the master, which was the chlorophyll, that's not good that it didn't open that. We'll have to look at that. We do have another release coming out, so we'll look at this, but for whatever reason, it's not opening the resultant band, but which it should. But yeah, so we'll have to look at that. That's it. So that's how the co-location tool works. And there's when it works. So we'll look into that. That subset, the mosaic tool, is a tool that you would use to combine many files together, which is a lot like the binning process. So I think it would take too long to talk about that tool. You can figure it out. The reproject tool is another way of reprojecting a single file, and that would probably be worthwhile to show. So with the reproject tool, if we take one of the source level 2 files that basically you can repeat what you had done, or alternatively do what you did with L2 bin and L3 mapgen. So so we have our input level 2 file, reproject. This is that Platte-Carré projection, or if I want to use the Lambert azimuthal eagle area, that's the one I used before. And then with this projection, you do have to define a latitude and longitude at the center. So you would define the values here. And then lastly, or not quite lastly, but you would you might not want to preserve the resolution. You might want to pick a specific resolution. That can be done here. And then now lastly is you can mask it. So this is a new feature to reprojection, which didn't exist in previous SeaDAS, is where you can actually apply the masks that were in the level 2 file when you reproject it. So that way you don't retain those bad aerosol values when you bring it over, because once you bring it over and you didn't mask it, then you have bad data and you don't know why it's bad because the masks are no longer there. And so I want to, probably running short of time, but I think it's important to address the issue about aerosols and getting potentially better retrievals. So if I too many products open, I'm gonna just close them and sort of start over on that mindset of handling the aerosols. So the options for aerosol is, you would first probably want to run level 2 gen and get out some of the aerosol products. So there's a couple aerosol products that are useful. So I did a standard run of level 2 gen and I picked these particular products. And if I take a look at chlorophyll and zoom in, and I see that these were the bad values. And then there's a thing called model max and model min, and it's actually using a blend of these two models, and these two models actually have numbers associated with them. And I may be going fast through this, but you can rewatch through this. But if let's say if I want to know, you can see how it's up here, the model numbers. There's 56 out here, but as you get in coastal, it changes the model numbers, and it's using two of them. So, and one of the ways of doing aerosol correction is doing a fixed aerosol, where you basically pick a single aerosol model and run with that. So I see that there's a variance of numbers. So what I can do is use the histogram plot. Right now I'm on aerosol model min. We won't get into what min and max means, but it's just that it's a blend of two models. And if I pick region of interest and I say, actually I didn't load this in, this is where it's important that you want to focus in on the area that you're concerned about. So I want to focus just on the Chesapeake. In fact, I'm not going to bother to load because you've seen that. I'm just going to draw a square here. So this little square is now my region of interest. And so what I'm trying to do is get an aerosol that works good in that area. So one of the ways is picking the models. So now that I have that region of interest, I'm going to do a histogram plot, and I'm going to go down here and pick my geometry. That's that little square that I wrote. It's called geometry. And if I run it, we see that model number 3 and 4 are used most commonly. There's a few of these other ones being used, but predominantly we've got model 3 and model 4 being used. And if we also look at model max, again, do the histogram plot, again, run it, and we see here model 2 and model 3. So we basically have 2, 3, and 4 are the models that we should consider. So then we just need to run level 2 gen for each of those models and see what happens. So to do that, go to level 2 gen and Go to processing options. This is where we have this aerosol opt. So aerosol opt has all these negative values, and that's a bunch of blends of mixed models. And one option is a single model. So to do a single model, you actually just give it the model number. So I'm going to just pick one of these so I can see the value, because you can't select that. But that aerosol option is right now -8, but I just did that so I would have it to edit. So what I want to do is I want to set it to 4. So what that's going to do is it's going to run my aerosols using option number 4. And then I would give it an output file name and some products as well. So I did that for model 3, 2, 3, and 4 based on my observations. So this is called using a fixed aerosol. So then if we go back to the output of what I ran here, which is model 2, 3, and 4, we open those up, and a reminder where we're coming from is here was, and we'll, for each one we need the land to get a bearing on this. So that's a retrieval from model 1. Don't really need this anymore, so I can come back. So if we put land on the mixed model, and we really should mask out the values so we're not deceived by that. There's the, and then there was ATM fail also had some. Is what we're looking for is the see what improvements we have in retrievals, and I'm going to put the no data layer just so I can compare this easier. So, and I think I can make, these are level 2. It's easier at level 3, but if you go to navigation and click this here, this should, I'm in the wrong mode here. I just drew on that, but that's okay. I think that, yeah, I think these will be synced up. Yeah, they are. All right, so we see our original was here. Using model number 2, we actually lose data, and actually it gave us a different value of chlorophyll, so that's not really a good model to use. But ultimately, when I went through for this particular one, when I use model 4, which I think I already opened, that one did look good. And so there's the chlorophyll. I'm going to go back to this band. Everything zoomed back out because it's all synced up. I'm going to add on the land, zoom in, and this is the Potomac here. So you see our original one is here, but using model 4, we gain some values definitely with the model 4. And then it's up to whether these, the validity of all these, darker values, that more research, but it definitely looks, fairly reasonable, going with the fixed aerosol for that region. The key is that when you do that, you've denoted a certain region, and it's going to cause elsewhere in your data to be off. So it's very much dependent on the region that you're picking and the aerosol content in that region. One thing you'll notice is that the coloring here is not colorblind compliant. It hits this bright green. So to make SeaDAS colorblind compliant, you go to General Color Manager, and here's the palette, and I'm doing it from scheme because like chlorophyll, each one has its own color scheme, but it's using a standard palette. So we go with universal palette, and if I say okay, then when I go back to color manager and reload this band, so now that's a colorblind compliant palette that's being used. So that's how you do the aerosol correction. And I'll do one last thing with the band maths. So let's take 2 files. I'm going to close all these, And we're going to open two files to compare with in band maths. I'm going to do mapped files. And what I'm going to do is take two files that are actually monthlies that I made with SeaDAS and did it the same approach that you would do it in the slide where I combined all those Olchi files. I had a bunch of, I went through each month and found about 6 files that were cloud free in the Chesapeake for each month. So this is July. And I'm going to, as I mentioned about the landmass, it is nice to have, but ideally you want to do this before opening these files. So I'm going to do that first, just so it's easier to talk to. So create land masks and nothing blew up. So here's July with the land. So this is many days in July that I have. There was 6 days that were cloud free, but that can be considered a monthly. And then let's look at November. November, you get a lot more retrievals than you do in the summer, and but the values are going to be slightly different naturally because it's the summer. So a nice thing to close on would be taking a look at the difference between summer and winter or November. So to do that, we want to pick a file to be in where we're going to make a new band. So we'll do it in November. Doesn't matter what file, but so right here is the make a new band. And what we'll do is edit expression and get rid of the current value. And so I want to do 100 times the July minus November divided by November. Say, okay, I'm not going to bother to name it this time. I'll just do a percent difference. But what I wanted to do is not make it virtual band. So what that's going to do is make it essentially it's standalone band. If I left it at virtual, then it's going to continually look at the other file, which is what I wanted to not have happen. So I make this new band. This is it here. So what I can do now is I'm looking for a difference here. So there's an anomalies plot. And what this does is this takes a while to build. Initially, when you load SeaDAS a session, there's this, you're seeing all these different palette images, and it takes a while for it to assemble all that. So there's just no progress bar to let you know that. So sometimes it's hard to know whether it froze or it's just thinking. So it was thinking. So I did an anomalies color bar, and now I just want to make my min and max sensible. So I'll do a minus 100 to positive 100. And then I'll go ahead and put the land on. So that's rather interesting results, because it shows that in the Chesapeake that the chlorophyll value has increased in July, and out here it's increased, but actually in other areas it's decreased. So I found that to be rather interesting to see the decrease that goes on as well. So that's an example of using the band mass to compare two bands, and you've actually just added, I know we saw that the co-location tool did not work, but this is a way that I actually was able to get a new band in here. And to end on one last thing, since the co-location tool didn't work, I'm going to go ahead and get my cyan band in here by a different means, and that's using the math band. So right now I have chlorophyll in here and I have my difference band. Let's go ahead and do band maths as a way to get the cyan bacteria into my file. So if you click the cyanobacteria file here, and in this case I'll name it, but cyano, and then do edit expression, and click over here, and I think I'm in the right file when I'm making it. We'll find out when I make it. I think I might be in the wrong file. I'm supposed to be here. Make sure I'm clicked on here, and when I do it one more time, because I think I was in the cyanobacteria file somehow. Sorry, that's the target product Yeah, you don't want to change it up here. You want to, so let me start over again. It's easy to, when you're, to click wrong button. So here's where you want to write it. So I don't want to change it here. I go into the expression and I want to click cyanobacteria and click that product, but delete the multiple clicks and the chlor A. So now we've got the cyanobacteria product here and cyano, give it a name, and now it's going to write it into the November file. So now it should work. Yes, it did. So now I have a file that has the cyanobacteria merged in with the chlorophyll along with my difference. And to polish that all off, we have now the file, and if we want to save it, so then we right click on it, we save. It's called a product in SeaDAS, but it's a file, so don't be thrown off by that. So you save this product as this. It's going to convert it to a beam dye map. You say okay, you tell it where to save it, and then you save this, and it'll save it. And then you can subsequently come back and open that file up, and you'll have all of those bands in there. And so I think there's plenty more that SeaDAS can do, and I really encourage you to download 9 as soon as it comes out, because it will have not only bug fixes, but will have up in the settings, you'll have a lot more preferences available to you. You can do preferences on the level 2 gen and level 2 ben. A lot of the OCSSW tools will have preferences. And it will also have the ability to, when you click on chlorophyll, like right now, when you click on chlorophyll, you get just chlorophyll, but it will actually be able to put like the grid lines and the color bar, like everything gets put on right away by default when you open it. That's a preferences setting, but it's a little bit more user friendly, and will of course be supporting the latest of PACE. So that wraps up the live demo, and can potentially add to the demo or answer questions at that time. So I thank you.
Well, thank you, Danny, for that wonderful presentation and demonstration. And here's what we learned today. I'm just going to summarize. So in this session, we went through SeaDAS 8.4.1. Daniel demonstrated it beautifully. We identified sensor data processing capability and workflow. We used OLCI as case study, but we saw workflow for many other sensors that you can use later on. We demoed Sentinel-3 OLCI data processing and analysis for the Chesapeake Bay region. You can choose any other region. You can do true color image display, level 2, level 3, data binning and mapping, can check quality flags. You can look at statistical and mathematical analysis of different bands. We also saw how to use OCSSW tool and analyzed and visualized chlorophyll concentration and remote sensing reflectances, specifically for OLCI. We also previewed plan for incorporating PACE data. PACE has already launched, and data will be available in a few months. So then we can analyze using SeaDAS. So again, here's a reminder that the homework is posted on the website and the training webpage. You can download, and answers must be submitted via Google Forms. There's also an exercise where you can get hands-on experience working with SeaDAS. And some of the questions involve taking screenshot of your SeaDAS window and sending as homework answers. So those who attended today's session and those who complete the homework assignment by deadline will receive a certificate of completion. So that concludes our presentation part. We want to acknowledge our OB-SeaDAS team. First of all, Daniel Knowles for the presentation, and also Ainur Abdulrazik and Bing Yang. They helped us in preparing presentation. Their help was very instrumental. They are the experts. We also want to thank other SeaDAS team members, Donald Shia, Sean Bailey, Alicia Scott, Wang, Koking Wang, and many other scientists are involved in developing algorithms that you use in SeaDAS. Here are some of the resources that you can refer to. The presentations as well as recording will be available on our website very soon. And here is the NASA Earth Data Forum. Any questions you have about either data or SeaDAS, you can post them there. And with that, I want to thank our ARSET team here. We have people helping us with editing and coordinating this training. So I want to acknowledge Brock Levins, Sarah Cashel, Selvin Hudson-Odoi, Natasha Johnson-Griffin, Sean McCartney, Susan Monty, and Jonathan O'Brien. All of them have helped in creating this training. So thanks, ARSET team, and thank you all for attending this session. We'll go to question and answer, and we have our SeaDAS experts here, so we'll be able to ask them questions and get answers. If we cannot post all the answers today, we will take care of them later, and then we'll post them on our website. So thank you very much, and I'll go back to Danny and Ainur and Bing for taking care of the Q&A. So we'll start with our question and answer session and see how many we can cover right now. Daniel, Ainur, and Bing, you can unmute yourself and reply to these answers. So let's start with question 1. How can we get help installing SeaDAS on a Windows machine? So of course, you can post this question on the Earth Data Forum, and SeaDAS team, please add anything you want to here.
We would like you to post the questions on the forum, because then that benefits other users too. And other users might actually chime in, with their experience. So that if you have a question, the best way is to ask a question on the forum.
Okay, great. Thank you, Bing. Second question is also related to SeaDAS on Windows environment. So yes, it works on the Windows machine, and processing works on Windows with Docker. Question 2. If you have any questions about that, you can post them on the forum. How about OCM3? So SeaDAS does not support OCM3 processing. Question 4, what are the possible applications of SeaDAS for atmospheric analysis? And SeaDAS team, you can add to this, but first of all, you can do atmospheric correction of optical images that you use for water quality monitoring. I also believe that since SeaDAS can open NetCDF files, you can get any atmospheric files and kind of do some of the analysis, but I would let SeaDAS team add to that.
The presentation covered aerosol corrections. So, I mean, SeaDAS does the atmospheric correction. So more details about atmospheric correction questions or would need to be more specific and can be addressed on the forum to understand what can be done. There's a lot that goes into it.
Question 5 is, what is meant by level 1 data? So
there's a slide on there earlier on, but level 1 data, when we think of level 1 data, it's the rawest. Well, there's level 0 as well, but it's unmapped. It's broad because you have level 1B and 1C, so that's gonna that would take some time to get in. I think the slides covered it some. There's on our web, there's some information about it, but the key is knowing that it's not the geophysical products aren't there yet, and depending on the sensor, it may not have geocoding either.
Also, the prerequisite from ARSET, what fundamentals of remote sensing, covers some of this, that what are different levels of data. Question 6, how many control points are required for vicarious calibration? So here's a reference, one of the earlier references about vicarious calibration that's provided here. In the literature, I've seen hundreds of points being used, but if there's any specific range, if you know, Danny or Bing, you can mention that here.
Well, I don't know specifically, but it's got to be valid data. So they're going to take as much as they can in order to understand that mission as early as possible, and then you know, apply that gain correction. It's not something that later would just continually change. It's because you still use the onboard calibrators. So it's basically if they don't get any control points, they can't vicariously calibrate until they do. So but they don't reject any control points.
So what is the advantage of using binned products compared to mapped?
Well, if you're using bin products, then as far as downloading the bin products, then as there's a slide on that mentioned that then when you map, you can map to different resolutions. So so it depends. If the map isn't what you want, then you would get the bin products. The map is like the end of the line for OCSSW processing, so you can't run processors further on that. If you're at the bin level, you can continually use level 3 bin. It's basically, it can serve as an input to other binners. So yeah, that sort of answers it as best I can on the you know, unless it's a little more specific question.
So question 8, it's again about installing SeaDAS, and it says ICOT remote server is down, OCSW is not accessible, please start OCSW remote server. How do I do that? And the answer from the SeaDAS team here is that after you install the SeaDAS processors through the Docker image or virtual machine, you need to make sure that the remote server is running. So it could have been down temporarily when you tried. Question 9, is it possible to run the SeaDAS on remote server or Ubuntu? So answer is the SeaDAS processors can be installed on a remote server and SeaDAS GUI can access them. We haven't tested running the whole SeaDAS application, the GUI part and the processors on a remote server. Question 10 is how do you input the letlon for the areas? So this is exactly, it's not sure what the question means. So if you can be more specific, otherwise letlon can be provided through several tools, and then you can answer this question.
Yeah, many tools use letlon, like a bounding area. You know, if it's like a level 2 extract level, any of the extractor tools, not reproject, mosaic tool will have area in it. There's tons of tools that have letlon like you can make masks with Latlon, so you could create, in the mask manager, a mask that is of the area, and then there's many ways that you can inject an area in there, including, there's a later question on it, but shape files. So you can import a shape file, and then that becomes a usable region of interest area mask.
Question 11 is, what are the specifications needed for the flagship step?
I've never heard of flagship step.
Right. So I think more clarification is needed. I'm not sure if you mean flags, then please be more precise. Question 12, SeaDAS installation in Windows 10 platform is asking some credentials. What shall I do? Please help. Again, I think you can post this on the forum. Question 13, what does it mean by level 1B file for MSI? Right now, only level 1C files are downloadable for Sentinel.
You don't need L1B file. When you do L2Gen, you MSI, you use L1C. Yeah, I don't know. Probably there's a typo on our slide.
Yeah, I think the level 1C was not mentioned, but that's what is used for MSI.
Yeah.
So question 14, when choosing products in the L2 Gen screen, how do I know which products might be conflicting? Danny?
Yeah, so that's the advantage of the product suites that are available when you start exploring products outside of those suites. Short of, that in the future, we'll do some more tutorials on specific products, but you can certainly ask on the forum. Some questions might, some products might be obvious, some not. If it's like ancillary things like sensor zenith angle, solar zenith angle, those aren't conflicting. But if it's products where you think there could be gains involved, other atmospheric correction being done differently, if you're thinking about mixing chlorophyll and a land product, well, chlorophyll isn't on land, so that intuitive thing might help, but ultimately there's buried inside OCSSW. There in the directories are some suites. It's like OCSSW share common and OCSSW. I forget where the path. But there's a hierarchy where it's like looking for suites, like the OC suite, and inside there is defines some of the gains and settings. So you could explore the directories. You don't have to go too deep. You just have to find the mission directories and go into those. And you would look at MSL12 defaults. That's what L2 Gen is using, and that's only going to help you though for suites that have been defined. So really, if you're looking for a product that is not the orientation of the spacecraft and things that are obvious, not associated with algorithms, it might be best to post a question on it on the forum.
Question 15 is, I'm a little confused. Are SR MODIS L2 data surface reflectance or remote surface reflectance data? And could you share a relevant publication? So MODIS data are surface reflectance. When you look at remote surface reflectance or remote sensing reflectance that we mentioned here, there is a ratio of flux going in and then coming out at the surface. So for proper definition, you can look at this ocean optic book. There's a description about different types of reflectances that we refer to. Question 16 is, what is bin data and L2 Gen? Could you explain in detail, please?
Well, there's some slides on there that we went over quickly, obviously. So the bin data, L2 Gen is a processor that takes, that goes from level 1 to level 2. So that's not mapping the data. Binning is the next step. That is your first step in mapping data. And it's bin data. Bins are, it's dividing the world up into equal area bins with a sinusoidal projection. And so those are special formatted files. And then you would subsequently map it. So I hopefully the presentation clarified that. There's a lot of details if you go to the slide on, there's 3 slides on the levels that should help a little bit on that concept.
Thank you. Question 17 is, how can I import satellite images into SeaDAS? So it's just go to File on top left, and there is Open Product underneath. So you can navigate to the file that you saved and open. Question 18, is it necessary to be connected to the internet for using ancillary files as an input? And yes, or you can get the, yeah, go ahead.
Yeah. Well, actually, I think you got it right. If you have downloaded them prior, if you've already run that particular day, then it has downloaded them onto your computer. And if they're on your computer, then it doesn't need to download them again. So if you know the days that you're gonna run, and you're not going to have internet, or just run for that week of days, and then you can go back and rerun when you're on some ship or somewhere where you don't have internet connection and you already have the ancillary data downloaded. So yeah, you don't need an internet connection, and that's really key for SeaDAS. And if otherwise, if you don't have internet connection, then you just can't use the ancillary files if you haven't downloaded them, but you could still run level 2 gen.
So question 19 is, what's the difference between L2 Gen and C2RCC? Which would be more appropriate over larger lakes like Lake Erie or the Great Lakes? Is the chlorophyll A product generated in L2 Gen from Sentinel-3 algae appropriate for large inland lakes like Lake Erie? So I am not aware of C2RCC. If you are Danny or anyone, you can say that. But as long as you can resolve pixels in any big lake, yes, you can use chlorophyll A products. So algae chlorophyll A products you can use for Lake Erie or Great Lakes, yes.
Yeah, I think I'm not sure, but I've seen C2RCC written on the Snap forum, so I believe it's one of the ESA processors.
Okay. We can provide you reference for that later on. And question 20.
Incidentally, before we move on, while I mentioned the Snap forum, that for OCSW, they're not doing OCSW over there, but the Snap shares a lot of the same tools with SeaDAS, like the reproject and subset tool and some of the visualization tools. And so it's also a good place to, if you're not looking at OCSW and looking at some of the other tools and have questions on those, it's a good reference to also go to that forum as well and see what people are posting there.
Yes, the forum is a very good resource because all the users can talk to each other and help solve some of the problems, such as installation and things like that. Question 20. I followed the video which was sent through this course email. I installed the Docker and SeaDAS in the window. I started to import the Hawkeye data in SeaDAS, but I couldn't do that. I was stuck here and I couldn't import any other imager either, so I couldn't go for further steps. Kindly help me with this. So I think Bing or Ainur or Denny, it says you do not need Docker to import data in SeaDAS. Please share the name of a Hawkeye file that you would like to import. So I think because you can visualize without Docker, I believe that's why, right?
No, you don't
Or at
need
least,
Docker to visualize. If you needed to import the
right.
Hawkeye file, you only need the CDAS platform, CDAS application, and it should be fairly straightforward. So I don't know why he cannot import it. So that's why I'm asking him to share the name of a Hawkeye file so I can take a look at it.
Thank you. So question 21, is Docker required for Mac or Linux users only? No, I don't think so. No, the Docker image is optional for Mac and Linux. It's only required for Windows. Question 22, can we use this platform for wetland water quality analysis? I believe you can, because there will be, you can see the water, but I'm not sure how accurate that would be. Any thoughts on that? Bing, Danny?
There's an NDVI product. I don't know if that's associated with this at all, but it's just within the limits of, what satellites are seeing and what algorithms we have available. Certainly the ROS is available for the whole Earth, but RRS and other things are limited. That'll get masked out.
Right, so I think you can get rows, and then from then on, you may be able to derive some relationship on your own. Question 23. Is there any option to import our study area as a shapefile? And it's, I think the SeaDAS team has provided the answer. It's yes, go to menu, file, import vector data as shapefile.
Yeah, and when you import that, then that gives you a mask inside there, and which we typically call a region of interest mask. It'll say ROI mask. So many of the tools use ROI masks. So that's the primary use of and you can also make a shapefile inside SeaDAS and export it. And I don't know. I think I did that in the video, in the demo. I can't remember, but you just draw it and then you export it, and then.
Yes, you did. And also in the homework exercise, you will be importing an Esri shapefile. It's a simple box, region of interest, but you will be doing that. Question 24 is, might be out of scope for this seminar, but I'm having trouble finding a good answers in documentation that I can find online. There are two Sentinel-3 OLG products for each scene over Lake Erie. One is Land Processing Center and MR1, Marine Reprocessing Center. These are specified in the file name, but are there any functional difference between the files? And if so, which would be better for Lake Erie? So
I don't recognize that.
No, I
It
think
might be something from ESA files.
Yeah, either NOAA or ESA. So I think we'll have to get back to you. We'll explore that a little bit and let you know. Question 25. Is there a way to check for sun glint contamination in scenes other than through visual inspection? And is there a way to correct for sun glint prior to modeling chlorophyll A concentration?
Well, at level 2, you have sun glint masks. There's several more questions on it. I saw. So there's a high glint and a moderate glint mask, and there's also thresholds that can be adjusted if you're running level 2 gen to affect when that glint gets triggered. So that's how you can mask it out, but you don't have to mask it out, and it's already got glint corrections, so you can just not use the flags. And when you're viewing a level 2 file, it's not masked out, so you actually by default, so you can see the but once you bin, then the defaults are to mask out at least high glint, if I remember correct. I don't think moderate glint gets masked out by default, but you can change that parameter within flag use. So that's when you go binning to mapping. But you can go well into the glint or chlorophyll. It's just then you have to think about whether it's compromised or not to the level that you don't want to use it. So it's a quality control issue at that point.
Okay, great, thank you. In question 26, what are the specifications needed for the flagship step? Again, I don't think that's very clear what you mean by flagship step. Also, is TSM an option as a derived geophysical parameter? I don't think total suspended matter is a derived parameter, a standard derived parameter in L2 Gen, correct?
Oh.
Yeah, I think turbidity is there, but total suspended matter, most likely not, but we can check. Question 27, does the coastline still overlay a raster, or is GSSHG vector data used? Same question for bathymetry and GEVCO data.
Well, when you use the coastline land tool, it creates both a vector layer and a mask raster layer. And say in the bathymetry tool creates topography and three bands it creates, and one mask. No vectors created for bathymetry.
So actually we are past our allocated time for this webinar. And we have many more questions to address. So what we're going to do is we will take care of these questions offline and post them on the training webpage. So we really want to thank you all for attending today's webinar, and special thanks to our SeaDAS team here, our speaker, Daniel Knowles, and then Ainur Abdurazik and Bing Yang. So thank you so much for your help with this training and answering all the questions. We will take care of all the questions which we have not been able to cover now, and we'll post that on our webpage. All the training material is on the webpage and homework as well. In the presentation, there's a whole appendix section where there are many slides that we did not cover, but they're quite informative, so you can refer to them. And as I mentioned earlier, this training is more or less a reference training that when we do our water quality training in future, ARSET does that, we will be relying on this SeaDAS training so to use some of the features that were discussed today. So thank you all very much, and thanks our ARSET team as well. Also, you will receive a survey from ARSET by email. So we request you to take care of the survey and provide your feedback to us. Thanks all. Anything from the SeaDAS team? If you want to add anything, please go ahead. But thank you all for being here and your help.
Yeah, thank you all, and thank you all for using SeaDAS, and please post your questions on the forum, and SeaDAS 9 will be out before PACE has data public, so we're busy on getting that ready for you all, so please update when that comes out. Thank you.
Which will be around the end of March, approximately.
Okay, great, thank you. Wonderful.
Yeah, it seems some people have problem with Docker installation. When you put your question, please be specific and try to attach the actual message to us. Also, make sure that you don't have network connection issues from your own system administrator side. You don't have a you don't have any issue with connection. For example, running a script. You have to have permission. So make sure you don't have any network issues first. And we are also we will provide a tutorial maybe for the Docker part to run through everything, the installation and configuration.
That would be great, actually. Yes. Yes. But I think once you go through the forum, you'll get enough feedback that you can install SeaDAS and Docker on the Windows machine. In any case, I think if you want to analyze level 2 data or view them, then you don't need that. Even on Windows, you can use SeaDAS without OCSSW, I believe.
Yeah, just opening a file and then analyzing, you don't need OCSW.
That's true, and the ESA mostly their developers use Windows, so they're mostly Windows based. So all the general tools are definitely Windows friendly.
Great, thank you all. Thanks so much.
Yeah, unless you want to process something, you don't need a Docker image installation before that step. So you can use SeaDAS for opening a file, look at the image and do the statistics analysis.
Great. Okay, thanks. Thanks again. Bye, everyone.